Namaskar, my dear friends. All right, so let us continue the discussion. We had reached up to like user IOs last time. So as you can see, we have been discussing S32K 118 microcontroller circuit design, and this is the microcontroller that has been taken 64 pin LQFP package from NXP. And what we'll do is we have already discussed about this particular microcontroller symbols and all these things and how to program and what are the like decoupling capacitors and everything, right? So what we'll start is we have already completed our power supplies, then some of the discrete parts, then we have completed our user IOs like push buttons, LEDs and touchpad, all those things, right? Now let us see. This is a particular like a circuit for ADC. So as you can see, we have used one multiplexer. So this multiplexer will help you to route your one of the signal to the output. Okay, so this is how it is going to work. So we have 8 inputs here like ambient sensor or temperature sensor, NTC, temperature sensor, humidity sensor and all the touchpad inputs. So these inputs need to go to your ADC. So instead of sending it to microcontroller ADC, what we have done is we have used microcontroller IOs to select the lines. Okay, one by one it will be selecting, and this is how the data will be going to the multiplexer, and this multiplexer will be coming as a input ADC to the input of your this circuit. Okay, and in this place what we are going to do is this is particular like I mean a op amp to be used as a buffer, then filter, then again buffer, and after that we have SPI interface ADC. So this is a very nice ADC with 16-bit output, and this is how it is going to get connected with your microcontroller. So microcontroller is acting as a like a host. So it is sending the clock signal as well as the chip select, and you are getting the data to that place. If you want to make it little bit better, what you can do is you can use one schematic trigger here, so that you can have a proper like data output. Okay. However, this will work, not a problem. So this was all about your ADC, external ADC that we have used 16B. All right, and it is having inbuilt voltage reference, so you don't have to give a separate voltage reference for this. Now this is the circuit that is used for, let us say one by one we'll start with. Okay. So this is my NTC. So NTC is going to be get connected to this particular like connector, and here you will be getting as a based on the temperature your resistance will vary, and this resistance variation will develop a voltage level here Vx. So this Vx will be changing, and this is how you will be getting some analog voltage at this particular temperature NTC, and this is going to go to your ADC. So this is how you will be measuring your temperature sensor based on the NTCs. All right. What I have done is I have given a provision for amplification as well. So if you want, you can amplify the signal. However, by default, it is used as a buffer. And then here it is filter. So this was all about NTC. Coming back to one of the photodiode is used for the purpose of ambient light sensor. So what is the ambient light, or what is like whether it is dark or bright. So based on that, this particular ambient sensor will be giving you the output, and after the filtering, like it is used as a integrator, and then you are going to get your output. So this output is going to give you as a like to go to the ADC to measure your ambient sense lighting. Okay. Now let's come back to the humidity sensor. So this is the humidity sensor that has been used from Renesas. So this is going to give you two outputs. One is your humidity sensor that is going to come up at the RH pin, and one is your temperature sensor which is going to come up at VT pin. Okay. So in detail, we have already explained this particular circuit in a separate video of humidity sensor interface. So humidity sensor, you can go and see that. However, this is the circuit completely. Now to send it to your ADC and all, we need to have like amplified and buffered and all those things. So what we have done is we have used two circuits here. So you can see here we have two circuits. So this Vt is going to come as input to this particular buffer. So this particular buffer is going to send it to the ADC. So temperature sensor ADC is going to come up like this. Coming back to the RH pin, so RH pin is also buffered and then filtered and then going to your external ADC, that is humidity sensor. Alright, so hope you have a good understanding about how to like interface your humidity sensor through a buffer and then filter, and what is the humidity sensor, how you can utilize it, that we have also shown it to you. Okay, so let us move to the next page. All right, so what we are going to do is after the ADC, yes, we have one micro USB. So micro USB is used to power up your device as well as to have a communication between your like a PC and the microcontroller board, like using your USB N, that is USB negative, and USB positive. We have used one ESD diode as well, which is in one package, like IO1 for your USB P, IO2 for your USB N, and VDD is for your V bus. Okay, in several of the like designs, I have also used ferrite bead at this place of around 220 ohm. So that also, if you want, you can utilize by referring other videos. Okay, it is having shield, so shield is directly connected to the ground itself right now, and with one of the like capacitor, it has been connected to your chassis. So this was all about your USB connector. Now coming back to the USB interface. So what is there is one of the very nice USB IC is used. Okay. So this USB IC is going to take UART signal as the input. Okay, and UART RX is output, UART TX is input, and this is how it is TXD and RXD. So this is a USB to UART bridge that is taken from a Silicon Lab, okay, Sci Lab. So this Sci Lab IC is going to convert your UART signal to your USB signal, okay. So this is how it is very easy to design. Some of the parts that I have like I skipped here is we have not used lot of like other parts like suspend, reset, and all those things. It's very simple. Just I have tried giving the power up and then you send it to your USB signal. So it's very simple design. Coming back to the other part, so same UART signal has been used for your RS422 communication as well. So if you want to utilize as RS422 communication, you can place these two resistors, and this is how it will be used. So one drive enable signal is used to drive this particular RS422 as a like a receiver or like transmitter that is driver. So when it is high, I mean by default it is going to be used as a transmitter. All right. So in RS422, this can act as a transmitter when RE and DE line both are high. So RE and DE line actually is made permanently high by using this particular pull-up resistor. Now if you want to convert it as a receiver, then it can be converted by putting it low. So if you want, you can use this resistor to make it permanently as a receiver in your circuit if you need to. Otherwise it can be controlled by your microcontroller IO as well. Okay, and this particular UART signal only is converted to your RS422 interfacing. Okay, now this is going to give you the differential output, like this A is your non-inverting output and this is inverting output. Okay, so this is how you will be getting A signal will be like this and B signal will be like this. So this is how the differential signal is making going to be very like a large difference. Okay, and one of the D sub 9 connector has been used for this particular purpose to communicate to your host PC. So hope you have now a very good understanding about this particular like circuit. So we have already completed USB to UART bridge, then we have completed RS422. Now let us get into the next part. So what we have done is, generally people utilize RS232 as well as RS485 for your long distance. Okay, this is for short distance and this is for long distance. So in that case what I have done is, in the same D sub 9 connector, okay, we have given a provision to go ahead with your RS232 conversion as well as, so this RS232 signal is coming from your UART. Similar to that, RS485 signal is coming from the same UART. Okay, so for this purpose what we have done is, we have used one analog switch. So this analog switch is going to take UART signal that is coming from your UART 1 pair and it is going to send it to your RS232TX as well as RS232RX. Okay, similar to that, if you want, you can send those signals to RS485TX and RS485RX by making your select line high or low. Okay, so right now it is low, and low means it is going to go to D1 and D2. So by default it is working as RS485. Okay, and if you want to convert it to RS232, then you have to make it high. Okay, good. So once it is connected, then what will happen is, one of these two ICs will be come into picture. Okay, so let us say 485 has come, RS485 has come. So RS485 will be acting as a transmitter right that time, and it is going to go. Similar to that, if you want this to act as a receiver, what will happen is, you have to just make this as low, and this is how it will be acting as a receiver. Similar to that, we have the UART to RS232 bridge. So this is also there from analog devices. This is also there from analog devices. Both the ICs are there from analog devices. Okay, and this particular analog switch is used from Texas Instruments. All right, so let us proceed next. Sometimes what happens is, we need to have lot of GPIOs so that we can control our LCD, or maybe keypad, or maybe like 7 segment displays or something like that. So in that case what I have done is, one of the SPI has been used with select line PCS2. So this is going to be acting as a interface line from this particular IO expander to your microcontroller, and this is how you are going to get your output signals here. So this 16 pin header can be used to interface your external LCD or keypad or all those things. Okay, we have given one reset button as well. So this particular IO expander can be reset, and we have lot of select lines. So if you want, what you can do is, you can connect several times of this particular IO expander based on the different address lines. Okay, so right now it is put as A2, A1, A0, and in that case you can see A2 is 0, A1 is 0, and A0 is 1. Okay, so it is going to be 001. So the address is 001 right now. Let's get into the CAN receiver now. So what I have done is, this is a CAN receiver. So in the CAN receiver, this CAN TX and CAN RX signal is coming from the controller, and they have been converted to some other voltage level. So VDD is used for 3.3 volt and VCC is 5 volt level, right? So 3.3 volt controller side logic level is coming and going to get converted to 5 volt levels. So this is how it is going to be CAN TXD, CAN RXD. Since this is a particular voltage translator with open drain, so that's the reason I have given separately pull up resistors. However, that is not needed because this IC is having inbuilt pull up resistors. Okay, so even if it is open drain IC, it does not require external pull up resistors. Okay, so NC means no connect, like you don't have to connect those resistors on your board. Now in the CAN transceiver, if you see, like I have used this CAN transceiver from Microchip Technology, because they are the like one of the best manufacturers for CAN transceiver. Even other ICs can be used, like NXP ICs are there. Then we have Texas Instruments, we have Renesas and all those things. So generally I prefer Microchip. Okay. All right. So we will be giving you circuits if there is a need using your NXP as well as TI. So what is done is this particular CAN FD is going to be used with this, and CAN H CAN L is there, which is going to go to your 4 pin header as the output. Okay. Similar to CAN, we have LIN transceiver these days. So LIN transceiver, what I have done is I have used a LIN transceiver IC from Microchip Technology only. Okay. So here we have UART signal, and similar to that, they can be directly going to your going to get converted to your LIN bus. And LIN bus is actually protected with TVS diode, and here also the input is also protected with like diode for reverse polarity and clamping diode for like ESD protection and all. Okay. And this particular 12 volt input is actually separately taken from your power supplies. Okay, so power supply is given to you in power supply section. You can see, I will show it to you now. So come back to the power supply section, how it is being used, because power supply was important. So we had plus 12 volt and minus 12 volt. I have not put it here anyway. Understood? Now the best part of this particular circuit design is what we have done is we have taken one of the clock out signal from your microcontroller, okay, MCU. So in that MCU, it will be generating one clock output, and this clock output is taken as a differential output. So this is kind of like low voltage differential signal, so LVDS driver. So this LVDS driver is going to get converting your clock signal to your differential output, and this can be taken to your 4 pin headers. So this can be driving your LVDS driver to some other clocks or something if you need. Coming back to the last part of this particular circuit design, so what we have done is we have one DAC 16-bit DAC. Okay, so this 16-bit DAC, this is the IC that is used, which is AD5543. Okay, so AD5543 is going to get interfaced with your SPI signals, and in this SPI signal you are going to get your output as current. Okay, so this current output is going to get converted to your like I to V converter, and this I to V converter is going to get converted by this AD8672. So for plus 5 volt you are going to get like 5 volt signal, and this 5 volt signal is made it as P5V. To supply to negative 5 voltage, we have simply used one like charge pump, that is ADM 8660. Okay, so this AD 8660 will be taking 5 volt as input, and it will be converting to minus 5 volt output with 100 milliampere of current. Okay. Now to drive the reference voltage, so this reference voltage is used as 3 volt reference. So what you can do is you can like utilize this particular reference voltage IC, that is ADR06. Okay, and this ADR06 can be used to supply the reference voltage here. And after that we have given one voltage shifting as well as amplification. So it is amplified 2 times. Okay, 2 times, and in that case you will be getting the output from minus 3 volt to 3 volt. Okay, so this is how you are going to go. If you want to have like minus 2.5 volt to 2.5 volt, in that case what you can do is you can supply the reference voltage to 2.5 volt. Okay, so this was all about the DAC circuit. Now let me show it to you the power supply that we have done for 12 volt and minus 12 volt, so that you can have that as a reference for your design. Okay. All right, so in our last circuit of like a 48 pin package IC, we had 12 volt power supply separately and minus 12 volt power supply separately. In that case, after the like filtering and having the capacitances as well as protection, we had P12 volt available. So if you want, you can do the same way for your 12 volt requirement. All right. So in this case, you can see we have the LIN transceiver here, and LIN transceiver require 12 volt. So if you are going to give your V in signal as 12 volt, it can be able to taking able to take very easily. This 12 volt actually can be taking from let us say 6 volt to 18 volt. So if you want, you can directly connect your voltage input V in itself to this particular P12V. Okay. Alright, so I hope you have complete idea of this particular block diagram and each of the sections of this particular circuit. And if you do have any questions regarding S32K 118 or 116 or 144 development ideas or their circuit requirement for your specific applications, you can put down your queries in the comment box and we shall be able to give you answers as soon as possible. Thank you guys.